Given a matrix n with a parameter k that's not equal to 4, and we're asked to find in terms of k the inverse. Right, that's step one of this question. There's then quite a lot more to do after. Okay, let's remember the inverse matrix is given by 1 over the determinant multiplied by the transpose of the cofactor matrix. Let's get the determinant. So for this, I'm going to expand along the first row, might as well. So it'll be k, and then of course we cross out the row and the column that k is in, and we're left with this determinant, 1, 1, 1, minus 1. And remember, it's a minus 5 because we're in the first row, second column. So minus 1 to the power of 3. That's how I always think about it, but you might have just learned that it's plus, then minus, plus, minus, etc. So 5, and then again, cross this out. We've got 1, 1, 2, minus 1. Take it steady. It's so easy to make a mistake. And then with the 7, it'd be plus 7. Cross out here. 1, 1, 2, 1. Right, expand the determinant. Going to get minus 1, so minus 2. And then minus 1, minus 2 gives minus 3. And 1 minus 2 gives minus 1. That's minus 2k plus 15 minus 7, which is 8 minus 2k. Now, the matrix wouldn't have an inverse if the determinant was 0, which is when k is equal to 4, which kind of links in nicely to what they said right at the start. If we're given that k is not equal to 4 to find the inverse. So we can be really confident we've got it correct, since you can see that it's just doesn't have an inverse when k is 4, which is linked in nicely here. Okay, let's get the cofactor matrix, then we'll worry about transposing it. I normally go straight for the cofactor. You could find a matrix of minors, but nah, let's just go for it. Literally every one of my videos where I do an inverse, I do this. Because it's not too bad. It's just remembering your pluses and your minuses. Okay, so first up, it's just like before, we're just going to be crossing that out, and I'm going to do it again. I know we've just worked some of them out, and you can kind of use it as a guide, but yeah, 1, 1, 1, minus 1. And then it's going to be a minus here. And we're going to get 1, 1, 2, minus 1. And again, a plus. It'll be 1, 1, 2, 1. Nice. And then we've got a minus here. 5, 7, 1, minus 1. Hopefully you're having a go at this alongside me, not just like watching me. Okay, get involved. Cross this out. K, 7, 2, minus 1. Then minus K, 5, 2, 1. And on to the last one. I'm going to speed it up now. You get 5, 7, 1, 1 minus K, 7, 1, 1 and K, 5, 1, 1. Okay, this gives minus 2, 3, minus 1. Then for the next one, we get minus 5, minus 7, but then we make it negative, so it becomes 12. Then minus k, minus 14. Then k minus 10, but the negative of that, so it becomes 10 minus k. 5 minus 7. K minus 7, but then made negative, so 7 minus k. And then k minus 5. Okay, we're pretty much there. So the inverse matrix is, remember, 1 over our determinant, so 1 over 8 minus 2k. Then we just multiply by the transpose, which, just to remind you, is when you reflect along this diagonal. So we're going to get minus 2, minus k minus 14, k minus 5, just like before. But then these two swap, so 12, 3, minus 1, minus 2, 7 minus k, 10 minus k. Nice one. Right, now for an application. Find in terms of P the coordinates of the point where the following planes intersect. We can turn this into a matrix equation. We'll get 2, 5, 7, 1, 1, 1, 2, 1, minus 1, multiplied by x, y, z. When you multiply this matrix out, you'll get precisely these equations, and then that will equal 1p2. And this matrix here is precisely M when k equals 2. So x, y, z, what we're going to do is we're going to pre-multiply both sides by the inverse matrix. The left-hand side will simply become x, y, z because the inverse times m becomes the identity. And then we're left with the inverse matrix on the right. Okay, and let's now sub in using k equal to 2 into here. So I'll get a quarter, and then minus 2, 3, minus 1, 12. This will become minus 16 when I sub in for 2. And then 8, minus 2, 5, and minus 3. We're multiplying, remember, by 1p2. Okay, now to multiply the matrix out, I decided to leave the quarter outside. And then we're going to get, remember, multiplying, so we're going to get minus 2 times 1 plus 12 times p plus minus 2 times 2. That ends up becoming 12p minus 6. Do the same along the other ones. You get minus 16p minus 13, because it's 3 minus 16, 3 times 1 plus minus 16 times p plus 5 times 2. Sorry, it should be a plus 13. I just realized it should be a plus 13. Good. And then the last one is minus 1 times 1 plus 8 times p plus minus 3 times 2. That ends up becoming 8p minus 7. And then we're asked for the coordinates of the point. So I'm just gonna leave it as a fraction, 12p minus 6 over 4. Of course, you could partially simplify it. Then 13 minus 16p over 4, 8p minus 7 over 4. Amazing. Right, we're not done. There's still a big chunk to this question. We're now asked to find the value of q for which the following planes intersect in a straight line. So not a single point, but a straight line. And here's the thing, k here is now equal to 4. So the inverse does not exist. We're moving away from being able to use matrix, the inverse matrix. We're going to have to deal with this without. So we've had like 3 planes intersecting at a single point, but now they're going to intersect along a straight line. So here's what it looks like. We've dealt with part B, where we got a unique solution, this point here, and now the planes might be intersecting like this, and there we go, a straight line. The determinant can be equal to 0, but we can still get a solution. That's what we're looking for here. Okay, and to do this, we just come back to our knowledge of simultaneous equations, and let's try and eliminate one of the unknowns. So when I did it, I decided to, first of all, deal with the equations that didn't involve q. So I took these two, and I decided to eliminate x. So I've got 4x plus 5y plus 7z equals 1. And I'm going to multiply this third one by 2 to get the x is the same. So 4x plus 2y minus 2z equals 4. Now I'm going to subtract. So 3y plus 9z is going to equal minus 3, which means y plus 3z is going to equal minus 1. Okay, that's the relationship between y and z, which must be true all the way along the line. And then I'm going to bring in q now, and I'll look at the second two equations just because they have, they've already got quite a lot in common, to be honest. So this time I'll times the second equation by 2, and that will give me 2x plus y, 2x plus 2y plus 2z equals 2q. And then this time I'll leave my other one the same and subtract them. So I'll get y plus 3z equals 2q minus 2. We've got the same y plus 3z. Brilliant. So it must be that these two are the same for everything to be consistent. Therefore, 2q minus 2 is equal to minus 1. 2q is equal to 1. Q is going to equal a half. This is, of course, not the only way to do it. We could have eliminated y. We could have eliminated z. There's other ways on top of that as well. So have a look at the mark scheme. But you can see the approach I've used has got us there pretty quickly. Now for the very last part, there's again lots of different ways to do it. So I'm just going to talk through how I did it. I've seen the solutions, they tried letting x equal lambda and then got y and z in terms of lambda. I don't know. I didn't really think to do it like that, and I kind of like how I did it, so I'm going to stick with it. So we've now got this line, remember, was y plus, I'm just going to write it down, y plus 3z equals minus 1. So all points on the line are going to satisfy that equation. And what I did is therefore is just find a point on the line. So let's go with z equaling 0. And then to consider a point on the line. And here's where I'm headed. I'm going to get a point on the line, and then I'm going to get another point on the line. And then I can construct position vectors from those, and hence find the direction vector on the line. Because here's the line, I'm going to get these 2 points. Here's O, I'm going to have this and this, and from that I can get this. That's what I'm talking about with my direction vector. And I've also been able to get onto the line here, so I can write down my vector equation, r equals a plus lambda b. This here is my b, my direction vector, and this is my a. Okay, that's our thinking process. So let z equal 0, then y is just going to equal minus 1. And then I can put it back into any of these. So, okay, which one should we put it back into? Yeah, this one. Now we know that q is a half. So x minus 1 is going to equal a half. Therefore, x is going to be 3 over 2. We've got ourselves a point. 0 minus 1. Sorry, not 0 first. Sorry, 3 over 2 minus 1, 0. Okay. And then let's just go with the next simplest. Let's go with z equals 1. I've just gone with z equals 1 because I'm timesing through by 3. Whereas if I went with y equals 1, I might get a fraction for z. I mean, I have got a fraction for x in the end, but it's okay. So z equals 1 is going to mean that y is equal to minus 4. And then I'm going to get x minus 4 plus 1 equal to a half. Therefore, x, that's minus 3. I'm going to add 3. I'm going to get 3.5 or 7 over 2. So 7 over 2 minus 4, 1. And what I've just found are these 2 points here. Okay, and therefore b is going to be the difference. It actually doesn't matter which way around I subtract. I'll just be getting a direction vector going in the opposite direction. So I'm not going to worry too much about that. I'll go with 7 over 2 minus 4, 1 minus 3 over 2 minus 1, 0. That ends up being 4 over 2 or 2, then minus 3 and 1. So, okay, we're basically there. R is going to equal, and I can pick either one of these now, 3 over 2 minus 1, 0. I can't just times that by anything, so I'm going to keep the fraction. I could, if I'd got a fraction here, I could times by whatever I wanted, because I'm now going to be timesing it by a parameter. So if I'd got like a half here, I could have made it 4 minus 6, 1. But I haven't. It's all good. So this is going to be our equation. Okay, and I think your answer is going to have that in it as a direction vector. There's a single direction vector. It might be going in the opposite direction. It might be minus 2, 3, minus 1. But there's actually lots of different ways to get on the line. So you might not have that as your answer. But hopefully you can sort of see, you can check the mark scheme to see if you have done it correctly. That is a nice approach for doing part 2. I believe a lot of people struggled with that in the real thing. It is just a bit different. You don't expect it with this matrix scenario, but here it is. So just want to say well done. I hope it all makes sense.